Hello friends, today we are going to learn about vibrational spectroscopy. After studying this module, you shall be able to conceptualize vibrational motion, study how a diatomic molecule acts as a simple harmonic oscillator, know the Schrödinger wave equation for a simple harmonic oscillator, learn about the vibrational energy levels in a diatomic molecule, and know the relative populations in vibrational energy levels of a diatomic molecule. Let us begin with the introduction. We have already learned about the rotational motion of a molecule, considering it as a rigid rotator, that is, where the bond is rigid and the bond length is fixed. However, this is only an approximation, as there is always some flexibility or elasticity associated with the bonds. One of the consequences of such elasticity of bonds is that atoms belonging to a molecule do not remain fixed at their positions, instead vibrate about their mean relative positions as shown in the video. Vibrational motion or oscillation consists of to and fro motion of a particle along the same path. In such a motion, the displacement of the particle from its mean equilibrium position varies periodically with time. If the motion has a fixed time period as well as fixed amplitude, the motion is said to be a simple harmonic motion. Few examples of simple harmonic motion in our day-to-day lives include a simple pendulum showing back and forth motion in small angles, a small mass tied to a weightless spring that exhibits movements along the same path, etc. Figure 1 depicts these examples. Since atoms in a molecule vibrate about their mean positions along a given bond with their bond angles as well as bond lengths changing periodically, such a motion can be considered as a simple harmonic motion. Let us begin with infrared or vibrational spectroscopy. We know that electromagnetic spectrum of light consists of different regions with varying frequencies and varying energies. Figure 2 depicts the electromagnetic spectrum of light. On the extreme right end, we have the radio waves, which have the highest wavelength and are least in energy. After that, we have the infrared region. After that, we have UV visible and then X-rays and then gamma rays in the increasing order of their frequency or energy. When rays from infrared region of an electromagnetic spectrum fall on the molecule, the vibrational energy of the molecule increases. This leads to the promotion of the molecule from lower vibrational energy levels to higher vibrational energy levels. Thus, we can say that a vibrational spectrum arises by virtue of transitions between various vibrational energy levels of a molecule upon absorption of energy in the infrared region. The essential criteria for a molecule to show such a spectrum is that there should occur a change in the configuration of the molecule, that is, change in the dipole moment of the molecule vis-a-vis a particular vibrational mode of motion. The vibrational spectra of the molecules are helpful in obtaining valuable information about the molecules in terms of their structure, symmetry, interactions, purity, bond strength, and various other physical parameters. We can also obtain important information about the elasticity of the bond undergoing vibrational motion, that is, the ease with which we can distort the bond length and the bond angle of the molecule from its mean equilibrium position. When the molecule absorbs infrared radiation from the electromagnetic spectrum of light, it not only brings about a change in the vibrational energy but also in the rotational energy of the molecule. This is because of the fact that infrared radiation is of higher frequency and thus higher energy than the microwave radiation that brings about a change in the rotational energy of the molecule. As a consequence, the rotational spectrum is superimposed upon the vibrational spectrum of the molecule, making latter complicated to study. One can obtain pure vibrational spectra by recording the spectra in the liquid state, where rotation of the molecules is hindered. In the gaseous state, however, the molecules undergo free rotation and vibration, thus giving a joint vibrational rotational spectra. We shall learn about this in the subsequent modules. In terms of classical mechanics, the vibrational motion of a molecule can be represented by taking a model system comprising of two balls of definite masses m1 and m2 connected to each other by an elastic spring. The two masses represent two atoms of a molecule, and the spring represents the elastic bond between these two atoms. As discussed above, such a system acts as a simple harmonic oscillator. The situation can be further simplified by considering a single ball of mass m attached to a rigid support by an elastic spring. When the mass is displaced from its equilibrium position, a restoring force acts in the opposite direction that tries to bring the mass back to its equilibrium position. If the displacement is small, that is, the extension or compression is less than 10% of the bond length of the molecules act as a simple harmonic oscillator and follow Hooke's law. That is, the restoring force is proportional to the displacement and it is acting in the opposite direction as the displacement, therefore a negative sign. When we remove the proportionality sign, we get a proportionality constant, that is F is equals to minus Kx as shown in equation 1, where F would be my restoring force, K will be the spring constant or the force constant, that is the characteristic of the spring and measures its stiffness. X is the displacement from the equilibrium position. The negative sign shows that the restoring force F acts in the direction opposite to the displacement in order to restore it to its original equilibrium position. When the mass is displaced from its equilibrium position, some work is done. This work gets stored in the body in the form of potential energy V. That is, we can write F is equals to minus dV by dx. That is our equation 2. Substituting equation 1 in equation 2, we get dV is minus of minus kx dx, or we can write dV is equals to kx dx. When we integrate this equation, we get V equals to half kx square. This is our equation 3. If we plot this potential energy V against displacement x from the equilibrium position, we get a parabolic curve as shown in figure 3. Figure 3 shows the potential energy of a simple harmonic oscillator. It can be seen that the variation of potential energy with displacement is a continuous function. This means that as per the principle of classical mechanics, the body can vibrate with any amount of potential energy. The above behavior can also be correlated with bond formation in a molecule. When two atoms approach each other during bond formation, there occurs repulsion between the two positively charged nuclei and also between the negatively charged electron clouds of the two atoms. In addition, there occurs attraction between the nucleus of one atom and the electrons of the other and vice versa. At an internuclear distance where these attractive forces balance out the repulsive forces, the energy of the molecule will be minimum and the said internuclear separation will be termed as equilibrium bond length or simply bond length. If we try to compress the bond and bring the atoms close to each other, that is, decrease the bond length, the repulsive forces will increase rapidly. Similarly, pulling the atoms apart in order to increase the bond length is also not favored due to loss in the attractive forces. Any change in the bond length therefore requires an input of energy. Thus, extension or compression of the bond can thus be easily compared to the behavior of a spring that acts as a simple harmonic oscillator and obeys Hooke's law. Figure 4 shows the distortion in a diatomic molecule in terms of extension and compression of a spring from its equilibrium position. We already know that the force required to displace the atoms from their equilibrium position is given by Newton's second law as given by equation 4 as F is equals to ma, which can be written as F is equals to ma, that can be written as m d square x upon dt square, where m is the mass of the body, a is its acceleration and x is the displacement from the equilibrium position. From equation 1, we already have F is equals to minus k times x. Combining the Hooke's law, that is equation 1, and Newton's equation of motion, that is equation 4, we get m d square x upon dt square is equals to minus kx, or d square x upon dt square plus k by m times x is equals to 0. Let this be our equation number 5. The general solution for above equation 5 is given by x is equal to a sine omega t, where x is the displacement from the equilibrium position, a is the maximum displacement of the vibrating particle from its mean position or the amplitude of vibration, and omega is the angular frequency of the vibrating particle. This can be further written as x is equals to a sine 2 pi nu classical times t, where nu classical is the classical frequency of the vibrating particle and t is the time period of vibration. This can be further written as x is equals to a sine under root k by m times t, where m is the mass of the body. Let this equation be our equation number 6. From the above equation 6, we see that vibrational motion of a simple diatomic molecule executing a simple harmonic motion varies sinusoidally with time. The time period taken for one oscillation is given by t equals to 2 pi under root m by k, as shown in equation number 7. The frequency of vibrational motion is defined as the number of oscillations taking place per unit time. The classical expression for the vibrational frequency is given by nu classical is equals to 1 by 2 pi under root k by m, as shown in equation 8. It was observed that the laws of classical mechanics could not explain the behavior of microscopic particles. Therefore, the correct treatment and correct expression for vibrational energy of a diatomic molecule had to be derived using quantum mechanics. On solving the appropriate Schrödinger wave equation, we get the vibrational energy of a diatomic molecule executing simple harmonic motion as EV is equals to V plus half h nu classical, as shown in equation 9, where EV is the vibrational energy, V is the vibrational quantum number which can have values from 0, 1, 2, 3, 4 and so on. H is the Planck's constant equals to 6.626 into 10 to the power minus 34 joule second, and nu classical, as earlier told, is the classical frequency of the vibrating particle. Substituting the value of classical vibrational frequency from equation 8 in equation 9, we get EV becomes equal to V plus half h by 2 pi under root k by m. Let this be our equation number 10. Since energy is given by the following expression also, EV is equals to hc nu bar as shown in equation 11, where h is the Planck's constant equals to 6.626 into 10 to the power minus 34 joules second. C is the speed of light equals to 2.999 into 10 to the power 8 meters per second, and nu bar is the wave number usually expressed in centimeter inverse units. The expression 11 can be substituted in equation 10 to get vibration energy in wave number units as E bar V in centimeter inverse. That is the vibrational energy in wave number units, that is I centimeter inverse, is equals to V plus half h by 2 pi into 1 by hc into under root k by m, or this can be written as E bar V in centimeter inverse is equals to V plus half into 1 by 2 pi c under root k by m as shown in equation 12, or E bar V in centimeter inverse is equals to V plus half nu c bar as shown in equation 13, where my nu c bar is equals to 1 by 2 pi c under root k by m as shown in equation 14. Here, E bar V is the vibrational energy in wave number units. V is the vibrational quantum number which can have values from 0, 1, 2, 3, 4 and so on. C is the speed of light which is equals to 2.999 into 10 to the power 8 meters per second. K is the force constant and m is the mass of the body. For a system with two masses m1 and m2, as in the case of a diatomic molecule, the mass in the above equation 14 is replaced by the reduced mass of the system. That is, we get nu c bar is equals to 1 by 2 pi c under root k by mu in equation 15, where mu is the reduced mass of the system given by m1 into m2 divided by m1 plus m2 as shown in equation 16. Equation 13 gives the expression for vibrational energy of a diatomic molecule acting as a simple harmonic oscillator and highlights one very important result, that vibrational energy of a harmonic oscillator is always quantized. This was contrary to the results obtained from classical mechanics, where the vibrational energy of a harmonic oscillator can vary continuously. The quantization emerges from the solution of Schrödinger wave equation due to the presence of vibrational quantum number V, which can take up only discrete values as 0, 1, 2, 3 and so on, and not any random values. Let us now look at the energy level pattern for a diatomic molecule. The various vibrational energy levels for a diatomic molecule acting as a simple harmonic oscillator can be obtained by substituting the values of vibrational quantum number V equal to 0, 1, 2, 3 and so on in the equation 13. Substituting the value of V equals to 0 in equation 13 will give us the lowest vibrational energy as E bar V is equals to 0 plus half nu c bar, or E bar V is equals to half nu c bar as shown in equation 17. Thus, we observe that the lowest vibrational energy is half nu c bar and not 0 as observed for a vibrating body using classical mechanics. This value of lowest energy is termed as 0 point energy for a simple harmonic oscillator. The fact that 0 point energy is non-zero means that atoms can never be at rest relative to each other. In fact, at absolute zero, when all the translational and rotational motion of the molecule ceases, the molecule still vibrates. Such an observation is in agreement with the Heisenberg uncertainty principle, which states that it is impossible to determine the precise values of position and momentum of a moving subatomic particle simultaneously. That is, delta x into delta px is greater than equals to h by 4 pi as depicted in equation 18. If the atoms are not moving at all and are at standstill, the uncertainty in position will be 0. This will give uncertainty in momentum as infinity as per the equation 18. In order to avoid such a situation, the atoms must have some uncertainty in position, which means that the atoms cannot be at standstill. They ought to be vibrating at their mean positions. This behavior is contrary to that obtained from the principles of classical mechanics, where the atoms of a diatomic molecule can be at standstill and can possess zero vibrational energy. Substituting the other values of vibrational quantum number V as 1, 2, 3 and so on in equation 13, we get the energy of higher vibrational energy levels as shown. For V equals to 1, E bar V comes out to be 3 by 2 nu c bar. For V equals to 2, E bar V is equals to 5 by 2 nu c bar. For V equals to 3, E bar V is equals to 7 by 2 nu c bar. For V equals to 4, E bar V is equals to 9 by 2 nu c bar and so on as shown in equations 19. The above results show that the energy values of a diatomic molecule acting as a simple harmonic oscillator are quantized and they cannot vary abruptly. In fact, it is the occurrence of these quantized vibrational energy levels that gives rise to vibrational spectra of the molecules, which again could not be explained by the principles of classical mechanics. On plotting these energy values on a parabolic curve, we get the various vibrational energy levels as shown in figure 5 below. Figure 5 shows the vibrational energy levels in a simple harmonic oscillator. We can conclude that a diatomic harmonic oscillator consists of equally spaced vibrational energy levels. The distance between any two consecutive vibrational energy levels can be calculated by the difference in their energy as delta E bar from 0 to 1 is equals to E bar 1 minus E bar 0, that is the vibrational energy for V equals to 1 level minus vibration energy for V equals to 0 level, which on substituting their values would be 3 by 2 nu c bar minus half nu c bar, and delta E bar from 0 to 1 comes out to be nu c bar. Similarly, if we calculate delta E bar from 1 to 2 vibrational energy level, that would be equal to the difference of E bar for V equals to 2 minus E bar for V equals to 1, and on substituting their respective values as 5 by 2 nu c bar minus 3 by 2 nu c bar, delta E bar for 1 to 2 comes out to be again nu c bar. Similarly, delta E bar for 2 to 3 would again come out to be nu c bar and so on. It can be seen that the distance between any two consecutive vibration energy levels remains the same throughout and has a constant value of nu c bar or hc nu c bar or h nu, as shown in figure 4, where nu is the frequency. Now let us do a simple question. A hydrogen molecule has a dissociation energy of 4.7 electron volts. Assuming it that behaves as a simple harmonic oscillator with frequency 1.30 into 10 to the power 14 Hz, determine the vibrational quantum number corresponding to the given dissociation energy. Let us see how we can solve this question. The given dissociation energy is 4.7 electron volts. We know that 1 electron volt is equals to 1.6 into 10 to the power minus 19 joules. Therefore, 4.7 electron volts becomes equal to 4.7 into 1.6 into 10 to the power minus 19 joules. The vibration energy for a simple harmonic oscillator as given by EV is equals to V plus half h nu classical. Substituting the given information, that is the given values, we get 4.7 into 1.6 into 10 to the power minus 19 joules is equals to V plus half into 6.626 into 10 to the power minus 34 joules second into 1.30 into 10 to the power 14 second inverse. On solving, V plus half is equals to 8.73 or V comes out to be 8.23, which can be approximated to a whole number value of 8. Thus, vibrational quantum number corresponding to the given dissociation energy is equal to 8. Now, let us look at the relative populations of vibration energy levels. Equation 20 shows the Boltzmann equation that gives the relative populations of energy levels as Nu by Nl is equals to e to the power minus delta E by kT, where Nu is the population in the upper energy level, Nl is the population in the lower energy level, delta E is the difference in energy between the two energy levels, K would be the Boltzmann constant equals to 1.38 into 10 to the power minus 23 joules per Kelvin, and T is the temperature in Kelvin. From the above equation 20, we find that relative population in the energy levels depend on the ratio of the difference in the energy between the two energy levels, that is delta E, and the thermal energy kT. If we look at the experimental data for most of the diatomic molecules, it is observed that the difference in the energy levels corresponding to V equals to 0 and V equals to 1, that is delta E from 0 to 1, has a value greater than the thermal energy kT at room temperature. Taking the representative examples of two common molecules, that is carbon monoxide and chlorine, we have the following data at 298 Kelvin. The thermal energy at room temperature, that is 298 Kelvin, that is kT, is equals to 4.1 into 10 to the power minus 21 joules. Delta E for 0 to 1 at this temperature for carbon monoxide is 42 into 10 to the power minus 21 joules, and for chlorine is 11 into 10 to the power minus 21 joules. If we substitute this data in the Boltzmann expression, we get N1 by N0, that is where our upper level is V equals to 1 and lower level is V equals to 0, is equals to e to the power minus delta E 0 to 1 by RT. On substituting the values, N1 by N0 comes out to be 3.6 into 10 to the power minus 5 for carbon monoxide and 6.8 into 10 to the power minus 2 for chlorine. Similarly, if we calculate delta E for 0 to 2, we get the value for carbon monoxide as 84 into 10 to the power minus 21 joules and 22 into 10 to the power minus 21 joules for chlorine. On substituting these values in the Boltzmann expression, we get N2 by N0 is equals to e to the power minus delta E for 0 to 2 by kT. This gives the value of 3.1 into 10 to the power minus 9 for carbon monoxide and 4.7 into 10 to the power minus 3 for chlorine. From the above data, it can be seen that the population at higher vibration energy levels corresponding to V equals to 1, 2 and further is very small relative to the population at the ground vibration energy level, that is V equals to 0. The population decreases as the value of vibrational quantum number V increases. In other words, we can conclude that at room temperature, most of the molecules would be present in ground vibrational state, that is V equals to 0. The transition of molecules from this V equals to 0 ground state will therefore be most intense as compared to the transition from other higher vibrational energy levels. The vibrational frequency corresponding to this transition from V equals to 0 to V equals to 1 is called fundamental vibrational frequency. In the next module, we shall learn about the selection rules for vibrational motion and vibrational spectra obtained for diatomic molecule executing a simple harmonic motion. We shall also learn about the mechanism of interaction of a vibrating particle with electromagnetic radiation and study the varied structural information that can be obtained from a vibrational spectrum. Let us now summarize what we have learned in this module. Atoms belonging to a molecule do not remain fixed at their positions, instead vibrate about their mean relative positions. Vibrational motion consists of to and fro motion of a particle along the same path. In such a motion, the displacement of particle from its mean equilibrium position varies periodically with time. When the vibrational motion has a fixed time period as well as fixed amplitude, the motion is said to be a simple harmonic motion. A diatomic molecule acts as a simple harmonic oscillator. Vibrational spectrum arises by virtue of transitions between various vibrational energy levels of a molecule upon absorption of energy in the infrared region. The essential criteria for a molecule to show vibrational spectrum is that there should occur a change in the configuration of the molecule, that is, change in the dipole moment of the molecule vis-a-vis a particular vibrational mode of motion. Pure vibrational spectra can be obtained by recording the spectra in the liquid state where rotation of the molecules is hindered. In the gaseous state, the molecules undergo free rotation and vibration, thus giving a joint vibrational rotational spectra. Vibrational energy of a diatomic molecule executing simple harmonic motion is given by EV is equals to V plus half h nu classical, or E bar V in centimeter inverse is equals to V plus half nu c bar, where nu c bar is equals to 1 by 2 pi c under root k by mu. 0 point energy of a simple harmonic oscillator is not zero and is given by half nu c bar. This is in agreement with the Heisenberg uncertainty principle. A diatomic simple harmonic oscillator consists of equally spaced vibration energy levels. The distance between any two consecutive vibration energy levels is the same throughout and has a constant value of nu c bar. Boltzmann equation gives the relative populations of energy levels. It is observed that the population at higher vibration energy levels is very small relative to the population at the ground vibration energy level. The vibrational frequency corresponding to the transition from V equals to 0 to V equals to 1 is called fundamental vibrational frequency and is the most intense transition.